Hey guys, this is Ms. Butcher, and this video is 5.8, Analyzing Graphs of Polynomial Functions. All right, so for any polynomial f of x, we've already learned all this, but when we find a solution or an answer, k, whatever that is, we can call it a zero of the polynomial, or we could call it a solution of f of x equals 0. It's a solution of the polynomial set equal to 0. It's an x-intercept, but we write that as an ordered pair. And then if k is your 0, x minus k is your factor. Remember, it's always x minus the 0 is always your factor. All right, so let's make a little table here, and let's start thinking about what polynomials look like. If the degree is 1, the highest power is 1, so 2x or 3x or 7x, then the graph is just a line, right? That's linear. We did that at the very beginning of the year. And a line turns no times. There are no turns. Let's think about if the degree is 2. If the highest power is 2, then it's a quadratic. Quadratics graph to be a parabola. And parabolas turn one time, right? You have this. There's one turn right there. All right. Suppose the degree was 3. When we graph that, you've probably seen it. It looks like some kind of an S-curve. Depends on the exaggeration of it, depends on the rest of the polynomial, but it's always some kind of curve like that with 2 turns at the most, right? And if we were to do degree 4, we might get something like this. That has 1, 2, 3 turns. And you would notice that whatever the degree is, so we use n for number, your turns are always going to be 1 less than that. So that's the key thing I'm trying to show you right here. A polynomial of degree n has at most n minus 1 turns. And I say at most because you could have less than that. For example, you might have seen some fourth powers that look kind of like this. That only turns twice. And that's okay, but it cannot have any more than n minus 1 turns. So here's an example. On your test, I am going to give you a question that's going to say how many turns at most will the function have? It should say at most. Sorry about the text there. So you will just, these are easy. You should all get these right. You should just look at the highest power, subtract 1, and write your answer down. Don't be tricked on this first one. The highest power is over here, but it's still the highest power is 5. So the second one here has 4 turns at the most. Easy, easy, easy. Don't forget about that, though. All right, for this next example, I'm going to talk about graphing these polynomials by hand. It gets kind of tough when we get into the higher powers, but because we know all of these things that we know about polynomials, like end behavior, and the number of turns, and the number of zeros, and how to find what the zeros are, we should be able to graph these polynomials by hand without a calculator. So here I've given you one that's already factored. So I've skipped the step of factoring it because we've spent a few days on that already. We know how to factor polynomials. But here we're going to graph this by hand. We have to think about what do we know about this. We know that there is 1 and then 2, 3 x's. So this is a third degree. So it's going to have at most 3 zeros and at most 2 turns. Because this is already factored, we can figure out what the zeros are very quickly. We're going to set each factor equal to 0. And we get x equals -2 and x equals 1. With a multiplicity of 2 there, so we know this is going to be a bounce. So I'm going to go ahead and start graphing this over here. I'm going to put a 0 at -2. I'm going to put 1 at x equals 1. And I know there's going to be a bounce there, so I just have to keep that in mind. The next thing I'm going to think about is the end behavior. We have to kind of imagine that we had this polynomial all fold back out. But if we did, we know that it would start with a negative. So we know that negative makes it fall on the right. I'm not going to write this properly. I'm just going to write falls right. And the fact that the degree is odd means it does the opposite, so it rises left. So what that tells me is that on my graph, I'm just going to put a little down arrow here and a little up arrow here, because it's not going to curve again or else it would cross the x-axis. So it's just going to go up from there and down from there. And I know it's going to turn at least twice in here. And I know this is a bounce, so I'm actually going to go ahead and put that there, the bounce. So that means I just need to figure out how far down this graph goes. And all I have to do for that now is plug in x values to figure out what the y values are. So we'll just make a table for the rest. We're just going to go with 0 and -1. If x is 0, then we have -0 plus 2 times 0 minus 1 all squared. Gives me -2 times -1 squared is 1, so -2. So right there. And then if x is -1, I have -1 plus 2 times -1 minus 1 all squared. -1 plus 2 is 1, so that's -1 times -1 minus 1 is -2 squared is 4, so that's -4, just down here. Can't reach it. Okay, so now we know that this graph is going to go down, at least down to here. Since I don't have a calculator, I don't expect it to be perfect, but we've got these points. These integer points should be perfect because I checked them out. I made a table with them, so this point, and this point at the bottom, and this one here. And so there's a rough sketch of what this would look like. We know that it's not going to do any weird fancy curves in here because we've got one curve at the bottom and one curve here, and we've already decided it could have at most 2. So it's not going to do any like extra curves underneath here. It's not going to do anything weird. It's not going to come up and down again in anywhere in any other place because it has at most 3 zeros, and we already found out that it was that one and then that one's a bounce. So there's no more zeros. It won't cross again. So we're, even with just these few points, we're pretty sure that this is close to correct. So now let's graph this exact same thing in the calculator. You're going to go to y equals. You're going to put it in. You don't even have to FOIL it out. You can just put it in exactly the way it was given to you, like this. And when you graph it, it should look a lot like this, what we've already drawn. You can find this bottom point, find out exactly where this bottom point's supposed to be, and this top point here, by doing second calc and then choosing maximum or minimum, because that doesn't just give you a vertex, that'll give you like a local maximum and a local minimum. So we could do that, and we would find out that our local max here, we call it local because it's not the max, the actual max is infinity, but the local max right here is at 1, 0. And the local min, that point down there, is actually at -1, -4. You can use your calculator to find those. So now let's do a word problem where you will want to use your calculator. This is actually in your textbook on page 389, but I thought it was a good example to talk through. It says you are making a rectangular box out of a 16-inch by 20-inch piece of cardboard. So yeah, say you need to make a box for a Christmas present and you don't have one. The box will be formed by making the cuts shown in the diagram and folding up the sides. So you're going to cut out the corners. Basically, this is going to get cut out and go away, and this in all 4 corners. If you just cut that away, then you can fold up the sides and make a pretty box. And those cuts are all going to be squares because if you didn't cut them perfect square, then the sides wouldn't match up. And you want it to have the greatest volume possible. Okay, so you have, I don't know, some ping pong balls that you want to put in this box, and you need to fit as many of them in as you possibly can. And the 16-inch by 20-inch piece of cardboard is all you've got. So how long should you make the cuts? What is the maximum volume, and what will the dimensions of the finished box be? All right, so we are going to set up an equation. It says down here, write a verbal model. You don't have to write a verbal model when you're solving these, but it is important to think through, what am I trying to do? And I know the volume of the box, and I know the dimensions because I know that volume is length times width times height, So I need to talk about my length and my width and my height. And I know that the height is x, right? Because if we're cutting x, that's x. I know that this width here was 16 inches, but then I cut away x and I cut away another x. So it's 16 minus 2 x's. And then this length here was 20, but I took away x and I took away another x, so 20 minus 2x. So my volume, V, we don't know what it is yet, is my length, 20 minus 2x, times my width, 16 minus 2x, times my height, x. And you could multiply that all out if it told you you had to have it in standard form. We'd rather have it in factored form anyway, just like this. And we can graph this. Now you could do it by hand, but I'm going to let you do it in the graphing calculator. You can just enter it in exactly as it shows right here into y equals, and let's look at the graph. It will look just like this. We can see that our zeros are going to be at 10 and 8 and 0, which they are. That's 0, that's 8, 2, 4, 6, 8, and that's 10. And this is a graph of the volume. That means our y-axis is the volume. And we want to maximize the volume. So, yes, your volume would be higher if you went up to infinity, but you can't go up to infinity because there's a limit here. You have to think about your real-world limits. Here's the picture of the box again, and you're cutting away x. And you could cut this much, or you could cut this much, or you could cut this much. But every time you cut that, you're cutting the same thing from each part, right? So at some point, you're going to get to where, actually here, because it has to be square, right? You're going to get to be where your cuts would overlap. Right here, they would overlap. So you cannot cut any more than half of this total length here. So 8 is going to be your maximum x value that you could possibly have. The least amount we could cut, oh, there's the bow. But anyway, the least amount we could cut is nothing because we're not going to cut negative. So that means that we're only looking at 0 to 8. So we're looking at from here to here. None of this is going to actually ever happen. So in this part, our maximum is this top here, which you can use your calculator, second calc maximum, and here's the values right here, which I've pretty much written all over, but it gives you x equals 2.945. And so that is how many inches you want your little cut to be to maximize your volume. And that's the end, and class is about to start. See you later.